Imagine you're 24 years old. You've just spent 2 years working through the most complex mathematical and spectroscopic data anyone has ever attempted to interpret from stellar light. You've stayed up through the nights running calculations by hand, and you've arrived at a conclusion so staggering it will, decades later, be called the foundation of modern astrophysics. The universe, you've discovered, is not made of rock and iron and metal, as everyone assumes. It's made almost entirely of hydrogen. Stars are hydrogen. The sun is hydrogen. Everything you see when you look up at the night sky is, at its core, the simplest element in the periodic table. You've cracked open the composition of the cosmos. And then the most eminent astronomer in the world reads your work and tells you that your conclusion is, quote, almost certainly not real. So you change it. You bury your own discovery in a footnote of uncertainty. You call your own results spurious. And then, 25 years later, the man who told you to do that publishes the same conclusion and gets most of the credit. This is the story of Cecilia Payne-Gaposchkin, and it's one of the most extraordinary and infuriating stories in the history of science. Cecilia Helena Payne was born in Wendover, England in 1900, a year that carries a certain symmetry given that she would spend her life at the threshold between the old world of astronomy and the new. Her father died when she was 4. Her mother, a painter and musician of considerable ability, raised Cecilia and her siblings with a decidedly unconventional independence. From an early age, Cecilia displayed what she would later describe as a compulsive, almost physical need to understand things. She taught herself Latin. She taught herself Greek. She memorized tables of logarithms for fun. At school, she encountered botany, and it briefly captured her, but then she encountered physics, and that was that. She won a scholarship to Newnham College, Cambridge in 1919. She arrived expecting to study botany. Then she attended a lecture by Arthur Eddington, the physicist who had just returned from his famous solar eclipse expedition, the one that confirmed Einstein's general theory of relativity. Eddington stood at the podium and described how he had watched starlight bend around the sun, and Cecilia Payne walked out of that lecture hall a different person. She switched to physics immediately. She was brilliant, completely, conspicuously, almost embarrassingly brilliant. Her tutors knew it. Her peers knew it. The problem was that Cambridge, in 1919, had no mechanism for knowing what to do with a brilliant woman. Women could attend Cambridge. Women could sit the exams. Women could pass the exams. But Cambridge did not award degrees to women, not until 1948. So Cecilia Payne sat her final examinations, performed at the top of her class, and received nothing. No degree, no credential, a certificate of completion basically, the academic equivalent of a thank you note. She had 2 options, stay in England in a system that had no official place for her, or leave. So she left. In 1923, she emigrated to the United States to work at Harvard College Observatory under the director Harlow Shapley. She would be the first person to earn a doctorate in astronomy from Radcliffe College, Harvard's women's college, since Harvard itself did not admit women to graduate programs. She was 25 years old when she submitted her thesis, and that thesis would turn out to be one of the most important documents in the history of modern science. Let's take a look at the problem Cecilia Payne was trying to solve. By the early 1920s, astronomers had developed a powerful tool for analyzing the chemical composition of stars, spectroscopy. When light from a star passes through a prism, it spreads into a spectrum, a rainbow of colors. We've all seen it. But embedded in that rainbow are dark lines, called absorption lines, that act like chemical fingerprints. Each element absorbs light at specific wavelengths, leaving its own unique signature in the spectrum. Astronomers had cataloged hundreds of these lines in stellar light. They knew stars contained iron, calcium, sodium, and dozens of other elements. What they did not know was how much of each element. And this, it turned out, was a much harder question. The standard assumption, reasonable on its face, was that the composition of stars was roughly similar to the composition of Earth, that stars were made of similar proportions of the same stuff, metals, minerals, oxygen, silicon. This assumption was so deeply embedded in the field that it was rarely questioned. It was treated essentially as a background fact about the universe. But Cecilia Payne questioned it. She had immersed herself in a new theoretical framework developed by the Indian physicist Meghnad Saha, the Saha ionization equation. Saha's work showed that the appearance of spectral lines in a star didn't just depend on how much of a given element was present. It also depended on the temperature of the star. At different temperatures, atoms lose different numbers of electrons, and an atom with missing electrons, an ion, absorbs light at totally different wavelengths than the neutral atom does. So the spectral lines you see in a star are the product both of composition and temperature acting together. This was the key nobody had noticed yet. Payne did the calculations. Painstakingly, systematically, she worked through the spectra of dozens of stars, applying Saha's ionization equations to tease out actual element abundances from the observed spectral lines. She accounted for temperature. She accounted for ionization states. She did this for 17 elements. And the numbers that came back were astonishing. For most elements, calcium, iron, silicon, the abundances were roughly what you'd expect, broadly comparable to what you'd find on Earth. But for two elements, hydrogen and helium, the numbers were not just slightly higher. They were higher by a factor of about 1 million. Hydrogen, according to her calculations, was not one of many elements in a star. It was almost everything. The sun was hydrogen with trace amounts of everything else as a kind of afterthought. She wrote it up. She submitted the thesis to the Harvard Observatory Annals. Before publication, Shapley sent it to the most prominent stellar astronomer in America for review, Henry Norris Russell at Princeton. Russell wrote back. His review was, in most respects, glowing. He called it the best doctoral thesis I have ever read, but he flagged her conclusion about hydrogen. The hydrogen abundance, he told her, was almost certainly not real. The idea that the sun was overwhelmingly composed of hydrogen seemed wildly inconsistent with everything astronomers believed about stellar composition. It defied physical intuition. It couldn't be right. And Cecilia Payne, 24 years old, newly arrived in a country not her own, working in a field that had never fully decided whether to welcome her, took the word of Henry Norris Russell over her own calculations. She added a line to her thesis. The apparently anomalous hydrogen abundance, she wrote, was almost certainly not real. She buried the most important discovery of her career in a sentence of false modesty. The thesis was published in 1925. Here's where it gets a little more complicated, and where it becomes about more than science. In the years following her thesis, Cecilia Payne continued working at Harvard. She produced a landmark study of stellar spectra. She developed new classification systems. She was, by any measure, one of the most productive and technically accomplished astronomers at the observatory. But her position there had a quality that her male colleagues' positions did not: precarity. Harvard did not officially employ her as an astronomer, not at first. She worked on Shapley's grants. She taught courses that didn't appear in the Harvard catalog because she wasn't official faculty. She trained students who would go on to careers with full academic standing, while she remained in an ill-defined institutional limbo. For years, the work she did was simply absorbed into the Harvard Observatory's output without formal recognition of her standing, and the hydrogen question sat quietly in the background. In 1929, 4 years after Payne's thesis, Henry Norris Russell published his own analysis of solar composition. Using spectroscopic data, and critically, the same theoretical framework Payne had used, he arrived at the same conclusion. The sun was overwhelmingly composed of hydrogen. He published it prominently in the Astrophysical Journal. He cited Payne's thesis, but the framing was clear. This was Russell's result, confirmed by new analysis. The discovery of hydrogen's stellar dominance entered the scientific literature with Russell's name primarily attached to it. This is not, it should be said, a story of deliberate, villainous suppression. Russell was not acting in calculated bad faith. He reviewed her thesis honestly with the priors of his era. He later acknowledged her priority, though quietly, in ways that did not reverberate through the field. The deeper mechanism at work was something subtler and in some ways more insidious, a system that was structurally arranged to route credit toward men and away from women, not because anyone sat down and designed it that way, but because that was the accumulated shape of institutional habit. Payne continued her career at Harvard. In 1934, she married the Russian astrophysicist Sergei Gaposchkin, becoming Payne-Gaposchkin. Together, they produced one of the most comprehensive surveys of variable stars ever compiled, over 1.25 million observations, analyzed largely by hand. The work was monumental. The recognition by the standards of the output was not. It was not until 1956, 31 years after her thesis, that Harvard appointed her as a full professor and named her chair of the astronomy department. She was the first woman to chair a department in Harvard's Faculty of Arts and Sciences, and it was long overdue. In the decades after her thesis was published, after the hydrogen question was settled, after the astrophysics community gradually absorbed the fact that she had gotten there first, the historical reassessment began. The astronomer Otto Struve, writing in the mid-20th century, called Payne's thesis undoubtedly the most brilliant PhD thesis ever written in astronomy. That assessment has become something close to consensus. The discovery that hydrogen is the dominant constituent of stars, and by extension of the observable universe, is not a minor finding. It's foundational. It reframes everything: how stars are born, how they age, how they die, why the sun shines. The whole stellar life cycle as we understand it is built on this fact, and the fact was Cecilia Payne's. She knew it too. In her autobiography, written late in life, she described the moment she saw what her calculations implied, and she described the moment she walked it back. There's something almost unbearable about reading her account of it, the casualness with which she accepted the correction, the lack of resistance. She'd been trained, by a decade of being the brilliant woman in rooms that weren't quite sure what to do with her, to defer. But she was also honest about what she felt, eventually, when the recognition came. She wrote, "The reward of the young scientist is the emotional thrill of being the first person in the history of the world to see something or to understand something. Nothing can take that away." That's either a statement of equanimity or a statement of grief, and probably both. So what can we conclude about this story? We could treat it as a tale of individual justice, and it is that, but it's also something more structural. Payne's case was not unique. It was one instance of a pattern that runs through the history of science with grim regularity. Rosalind Franklin and the double helix, Jocelyn Bell Burnell and the pulsar, Lise Meitner and nuclear fission, Alice Ball's leprosy treatment, which we covered in an earlier video. In each case, a woman does the foundational work. In each case, the credit migrates elsewhere. The mechanism is rarely conspiracy. It's usually something quieter: a review board with assumptions, a supervisor who doesn't push back, an institution with no formal slot for a woman's contribution. The effect is the same regardless of the mechanism, and the consequence for science is real. We don't just lose recognition when this happens. We lose the signal that tells young women the field is for them. We lose the work they might have done. We lose the versions of Cecilia Payne who saw what happened to her and decided, wisely and rationally, that the cost was too high. Cecilia Payne-Gaposchkin died in 1979 in Cambridge, Massachusetts, not the Cambridge where she had been brilliant and been given nothing, but the Cambridge where she had spent most of her adult life and eventually been given, if not everything, then at least something real. The universe is mostly hydrogen. She knew that before anyone else. She was told she was wrong. She outlasted the people who told her that. She saw her work vindicated, her name attached partially and belatedly to one of the great discoveries in the history of science. And she kept working the whole time. 1.25 million observations, an enormous career. Students trained, papers written, spectra analyzed.